step number 6, that is root locus is symmetrical with respect to the real axis. Up to this particular stage we have discussed. So now here to find the breakaway point, we need to have the characteristic equation. So when you are understanding the characteristic equation, so you can understand that. Okay, so the system characteristic equation is given by 1 plus j of s into h of s equal to. So you substitute the equation values, and then will get this particular thing, that is the breakaway point. The system you will get the k value equal to minus of s cube plus 6s square plus 12s equal to this one equal to k you will get. Okay. So all of you just do it and confirm. So how many of you done this particular step? Please raise your hands. Rajesh, have you taken? So I'm able to tell. Okay. So now after the you doing this particular thing, okay. So we can go for this particular understanding, that is to find the angle of departure for the complex pole. So this is a very important step. You please all of you take down this one. So how to find out the angle of departure for the complex pole? Okay. So how to find the angle of departure for complex pole? We'll see now. The first step is saying that to find the angle of departure for the complex pole. So phi d. Okay, so phi d. So be the angle of to complex pole. Let phi d be the angle of departure. So phi d represent what? Angle of departure. So here there is only one complex pole. So what is that particular complex pole? It is minus 3 plus or plus j root 3. Okay. So here when you're talking about the complex pole, that is minus 3 plus j root 3 if you take, okay. So you will get like find that one pole, which is at what you call for that the concepts in that so all exists. Okay, so I can understand the thing. Okay, so phi p2. So when you're talking about the complex pole, so what is that particular complex pole? It is given the value. It is 180 degree minus 1 tan inverse of square root of 3 divided by 3. So here imaginary part divided by real part. Okay, so imaginary part is root 3, real part is what? 3. So that is how we are going to find out the angle. So 180 degree minus of because minus sign is there. So minus of tan 180 degree minus tan inverse of this one will come. So it will come like 150 degrees. It will come. Okay. So once it comes 150 degrees, so phi d will be equal to 180 the formula 180 degree minus summation of all pole angle of all poles. So minus summation of all zeros angle of all zeros. So if you take this particular scenario, so what exactly we will get is phi d will be equal to so phi d will be. So now here what is the thing is of departure if two poles are going to take it up. Okay, so when you're talking when it so we must take in such a way that okay, so here minus 3 plus j root 3 we have taken. There are another root that is minus 3 minus j root 3 also it is there. But when you are considering this particular scenario with respect to the calculation purpose, so we are finding out for first 1 rule 1 pole at every time. So when we are considering 1 pole for every time, okay, so there is a normal poles are there, no? So that particular poles also we need to consider. There is a 90 degree we need to consider the normal pole. So that particular pole along with the pole of this particular thing. So that angle we need to consider. So once we consider these two angles, so we get the phi d equal to so and so minus 60 degree. So therefore the angle of departure of complex pole at s equal to minus 3 minus j root 3. So phi d dash will be equal to, see here what exactly happened. Once you calculate for one complex root, it is minus 3 plus j root 3. You need not to calculate for minus 3 minus j root 3. So you just take the negative of that one. It will come next angle. That is if 1 minus 60 degree is one angle of departure for one complex pole. So reverse is minus reverse is 60 degree you are going to get. So doubt in this one, you can ask me. Or else you can go for the next step. Do you have any doubt in this one? Shall we go for the next one? Can you now please reply me, respond me at least? You understood or not understood? Anyone, any response, you please make it. Any one of you. Vaishnavi, Varshita, Manish, Manoj BC, Manoj HM, Manoj Deep.
Understanding, sir.
Next, we have step number 9. So in the step number 9, you can see that once again we are going for finding out the angle of the point of intersection. So here to find the intersection point of locus on j omega axis and the range of k for closed loop stability. The system characteristic equation is given by s cube plus x square plus 12s plus k equal to 0. So here putting s equal to j omega. So in the above equation we'll get minus j omega cube minus 6 omega square plus 12 j omega plus k equal to 0 is the equation we get. So once we get this particular equation, so k minus 6 omega square plus j into 12 omega minus omega cube. So this is the what exactly the value we'll get. So if upon solving this one, so k equal to 6 omega square. So k value comes like 12. Okay, so k value will comes like 12 will be equal to omega square. So omega will equal to plus or minus root 12. So omega square is equal to 12. So k value will come like 6 into 12, that is 72 we will get. So all of you calculate it and tell me whether you get the same answer or not. I'll give you 2 minutes of time. Complete this step.
Yes, sir.
After we divide 72. So the 72, I can understand one thing, that the 72 is the k value, that is the for closed loop stability, that is 0 to k. So 0 less than k less than 72. That means what, up to the range of 72. So the system is called as what, conditionally stable. And omega will be equal to plus or minus square root of 12. So now we will take this particular scenario of plotting the root locus for this particular numerical. Okay. So you can see that complete root locus for this one. So we will take this particular opportunity, that means what, I will take the x-axis and we'll take the y-axis. Okay, so you can able to write this particular root locus, all of you. So if this is the S-plane, okay, so if this is the S-plane, so in this so pole dimension, what's the way exactly the poles are there? One is at origin, that is k equal to infinity. So this is the origin pole. So next pole is what, minus j root. That means what, here minus 3 means what, negative side, that is left hand side. Plus j root 3 means what, particular sheet, that is it may come here. Similarly, minus 3 also k equal to 0. That is what that is where we have mentioned this particular thing. Okay. So asking this particular thing. Okay. So we need to write the breakaway point. Where exactly the breakaway point is coming? Okay. So here breakaway point will come in the place centroid. Okay, centroid will mention. So where is the centroid? Centroid is that, we'll see that one. Where is the centroid? So centroid place is also at -2. So centroid is also at -2, as well as breakaway point is also at -2. Okay, so equal to -2 is the place where breakaway point as well as centroid both are coming in the same position. So now after that one, in the centroid, so there is a two angles. So one angle is what? So you can see that asymptote 60 degree, 180 degree, 300 degree. So 60 degree means like this. So whatever the angle which is going upside, no? So this particular angle, this particular portion, you can see that 60 degree it is going. So 180 degree means exactly in the left to the line. So in the 300 degree means what, positive side. So it is coming in this particular bottom. Okay. So that is where, and that is how it is going to end. So now once we done this particular thing, that is breakaway points, central. So later breakaway point we are going to mention in this particular part only. This is equal to -2. So once we do the marking of this one, okay, breakaway point. So now we are going to consider the angle of departure. So angle of departure, okay, so -60 degrees. So -60 degree if you take, so and if you just cross that particular breakaway point here, okay, and it will show that 300 degrees line is there, no? So it will give the direction. So you need to go in the same direction. So you can see that -60 degree is equal to 300 degrees. So here from the pole to the breakaway point, we come with the -60 degree only. So after -60 degree, once it comes, it has to go till the end point of intersection. So till that particular stage, that particular angle will be indicated by asymptote. Asymptote is saying that 300 degrees you go. So 300 degrees when I'm going, so I have to take the same path. That is why dotted lines are not visible. Okay, this has been masked. I can say. That means what, on the dotted lines we are written the within the thick lines, so the dotted lines are not visible. So it will come down. So once it is coming down, it will come like this. Okay, so j omega. So it will touch here. It is minus j12. Similarly, from the angle of departure from the bottom line plus 60 degree, it will go up. So once it reaches this particular point, it is showing the next path, that is 60 degrees. So it will go up like this, and it will meet j root 12. It will go and meet that j root 12. So this is here. So this is how it this order of a root is saying. So in the range of 0 to 72, above the 72, we can say that the system is not stable. The root locus is not stable. Here, so you please make a note of this particular thing, all of you. So all of you please write this particular root locus diagram. So if anybody got any doubt, please ask me. So I'll explain it once again. So I'll give you 2 minutes of time. Please write this particular diagram and analyze this one. And if you get any doubt, please ask me. So that completes your root locus part. Okay. So I just go for the next part. So next, take the heading frequency domain analysis. Okay, frequency domain analysis. So in the frequency domain analysis, so once you take the heading, the frequency domain analysis, so you can understand the thing that time response of a system is usually more difficult, okay, to determine analytically, especially in the higher order system. See, when the system is getting complex with respect to the order of the system, it means second order, you can plot the root locus. So when it comes to the higher order, okay, so to determine and to analyze the system, it is very difficult. So when it comes to the analyzing part and once it becomes difficult, so the time domain specifications and time domain analysis is very difficult. So we need to find the alternative. So what is that particular alternative is saying? So alternative is saying that you can go for the next alternative, that is frequency domain analysis. So once we go for the frequency domain analysis, so what is the difference? What is exactly the similarity? So we have to understand what is the similarity also. We need to understand what is the differences also. So once we understand this particular two things, okay, so we can able to uh, frame the conclusion lines. So where exactly it is happening? Okay, so how exactly the things are working? Okay, more difficult to determine analytically, especially for the higher order system. So in frequency domain, there are graphical equivalent for control system to meet the various time domain specifications. So there are good numbers like Bode plot is there, like a polar plot, like a Nyquist plot and all it is there. So those are with respect to the frequency domain. Okay. So now in the time domain, the root locus plot is there. Okay. So or else I can say that RH criteria analysis is there. So yeah, computing response the two important things we need to understand. What are the two important things? Computing frequency response for the range of frequency omega is useful for identifying the system transfer function. That is the first thing. Second thing is what the time domain switching the frequency domain case. So these are also advantage. So when what you call for that analyzing the time domain specifications from the frequency, so then we can go for the frequency domain only. So here you can see that a frequency domain specification, that is resonant peak. So MR, resonant frequency omega R, and bandwidth BW is the three things we need to understand. So now the particular thing once again we are talking about the what is called for that prototype of the second order figure this particular thing. RFS and CFS, between RFS and CFS omega n squared divided by P. Okay, which is available. So here also in the frequency domain also we consider this one only. So once we consider this one, we need to do this particular process, that is the closed loop transfer function is given by T of S is equal to C of S divided by R of S into omega, that is equal to omega squared divided by same equation. So like what we have taken in the time domain, so the same equation you can table to take here also. So now here one thing we need to understand. The frequency response is obtained by letting S equal to j omega. Okay, S equal to j omega. Accordingly, so T of j omega is equal to, okay, so C of j omega divided by R of j omega. So one should take this particular scenario. Okay. So we can say that put S equal to j omega. That's all. Nothing else we are doing. So wherever you find S, you put S equal to j omega. divided by j omega plus 2 delta omega n j omega n plus omega n square will get. So you just do it accordingly. So you will get like okay. So this equation you are going to get. All of you do it and tell me whether you will get the same answer. So once you get this one, you'll reframe the equation with respect to the our required format. So we'll take the normal frequency divided by natural frequency. That is angular frequency divided by natural frequency omega by omega n. That we'll consider as the u. So once we consider that as u, so the equation will be formatting with respect to this particular format. Okay, the equation will become like this. Please see to it. So your magnitude and phase response, I'm able to see that the magnitude and phase and frequency response are m equal to so and so it is been coming. So your magnitude response, you can see that magnitude will be given by m. So m of m will be equal to modulus of t of j omega. So you take the modulus on both sides, that is on the new 1 by 2 to the power of 1 by 2. So where u is less than 1. And similarly, when omega, that is phi angle will be equal to what? Tan inverse of minus tan inverse of 2 delta u divided by 1 minus u square. That is what you call for that. We say that real part, imaginary part divided by real part. And when u greater than 0, that is minus 180 degree plus of tan inverse of the equation is going to change. So these two are the just equation from the observation we have written this one. So you please copy these particular equations. So after that, you can see that the variation of M and phi. So when delta is less than 0.7 is given by So next is what a phase. So you can see that in the x-axis we have taken the n, and in the y-axis we have taken the degrees. Okay. So how the particular phase variations is going to happen, that is also been explained here. You can go through it. So when you're talking about the resonant peak, okay, so here MR is a maximum value of M, so T of j omega. So MR is a good measure of relative stability of a closed loop system. A large MR corresponds to a large overshoot, so in a transient response. So that many practical control systems are designed with MR, that is a peak overshoot. A resonant peak will be equal to 1.1 to 1.15, sorry, 1.1 to 1.5. So this is what exactly the thing. Similarly, when we are talking about the resonant frequency omega r, so omega r is a frequency at which a peak resonates. So peak resonance will occur. Okay, so it is a good measure of speed of the system. So the quicker the response, faster the system. That's all. Similarly, the next definition is bandwidth. So bandwidth is the frequency at which the magnitude m drops to 0.707 of 707 of 1 or 3 dB down from its 0. So that is what exactly the thing which is going to happen. So when you're talking about the cutoff rate, the shape of the magnitude curve is called as what cutoff rate. So the shape of the magnitude curve itself is a cutoff rate, we can say. So all these things we'll understand from the graph. Okay, so here the expressions wise, you can see that the expressions for omega mr comma omega r, okay, and bandwidth. So what exactly the equation you will get? So we know that m is equal to so and so we already taken. So now resonant frequency determined by the derivative of m with respect to the u to 0 and equate to 0. So when you do this particular thing, so we'll get the 4u into u square minus 1 plus 2 delta square equal to 0 we'll get. So when u equal to ur, so and so derivations you need to do it. Okay, so u equal to ur, roots of the above equation. So you find that omega r will be equal to omega n into square root of 1 minus 2 delta square. So here also omega n, here also delta square will come into picture in frequency domain also. The only thing is what the equations are going to be somewhat slight difference will be there. Okay. So we can go through it, this particular equation. The angular frequency is always a real quantity. So hence 2 delta square should be less than 1. Okay, so in other words, for delta greater than or equal to 0.707, the resonant frequency is omega r equal to 0 and mr equal to 1. So for delta equal to delta less than 0.707, the peak resonant is mr equal to m into u into ur. So mr will be replaced with m, so that means what m will be replaced with mr. Mr represent what? Resonant, okay, nothing else. So we get the equation mr equal to 1 divided by 2 delta into square root of 1 minus delta square. See, these derivations are very much similar to the previous derivations what we have done for the time domain specifications. this particular equation, at least you take it down. Okay, bandwidth equal to what? What is the equation for bandwidth? Bandwidth equal to omega n into 1 minus 2 delta square. So plus 4 into plus square root of 4 delta to the power of 4 minus 4 delta square plus 2 whole to the power of 1 by 2. So this particular equation, see, derivations and all you can able to go through it, and if you find any difficulty in it, you please ask me. Equations you please write it down so that we can go for the numerical analysis. So this bandwidth equal to what? The equation, and MR equal to what? That equation, this equation also you please write down. So after writing this one, I can go for the numerical. So write down all of you. The negative feedback control system, which is characterized by g of s into g of s equal to k divided by s into s plus alpha. So h of s equal to 1. So copy this particular question and try to solve this one, all of you. After taking this equation, please tell me. So after doing this one, you can go for the system characteristic equation finding out, and as well as you can find out what is the value of alpha as well as what is the value of k or omega n square. So you please do everything in the next class, and we'll see you in the next class. Thank you. Bye. You can all leave.
Thank you, sir.